All right, so today I'm going to be talking to you about ROC, receiver operating characteristic. I'm pretty sure that most of you have attended such sessions or you know about it. But before I start, I would like to know what do you know about ROCs? So who can tell me?
It's a way to measure how sensitive a certain test is, or how
Okay.
results, how applicable they might be.
Okay. And what's the curve about?
Curve?
Yeah.
It's in a curve form.
Sensitivity
versus
specificity.
Okay. One?
One likelihood ratios.
Okay.
So basically, whenever you calculate, they present it on this graph.
Okay. So is it one cutoff point that you have?
Not necessarily.
Is it sensitivity versus specificity in
Mhm.
terms of plotting?
Okay. Sure. Yeah. So let us go through it. We'll build the basics and then we'll talk about the ROC in more detail. So basically, it's a graphical plot which illustrates the performance of a binary classifier system as its discrimination threshold is varied. So what do you mean by discrimination threshold? So different cutoff points, right? So it is how does the test performs as we change the cutoff point between positive and negative. Exactly. So basically, we are dividing it into a binary classifier, positive, negative, but using different cutoff points, we'll have different positives and negatives, and eventually each cutoff point will indicate a certain specificity and sensitivity, and accordingly to have a visual impact or visual picture about what's going on, we plot it in a curve, and this is what the ROC is. Effective method of evaluating the performance of a diagnostic test. And ROC analysis is related in a direct and natural way to cost-benefit analysis of diagnostic decision-making. Why cost-benefit analysis? So how would it be directly related to the cost-benefit of the diagnostic testing?
For example, we might want to determine a preset cost and see how it changes if we change the cost, and vice versa. If we have a certain benefit we see.
Okay. Anybody else?
Since we are aiming towards the highest specificity and sensitivity in terms of the diagnostic test to have the optimal performance,
Okay.
it's related as well to when we have this high rates, we are able to have the best benefit at the lowest cost, for example.
All right, so it is basically related to the fact that when you manipulate the cutoff point, you might end up with lower sensitivity as compared to specificity, or the other way around. So sometimes any cutoff point that you adopt might affect your cost. How many people you are missing who are positives, and how many you are missing and they are negatives, or the false positive and the false negative. So that's why it's related to the cost benefit, and it has to be taken into consideration. So first developed by electrical engineers and...
Can I say one more thing?
Yes, sure.
I thought of something completely different.
Yeah.
So once you choose that whatever cutoff you want, that's the best combination for you, you're going to treat people, if it's a desirable level, who are below that cutoff or above that cutoff, depending what you're talking about, and therefore there will be cost effectiveness involved too, because it's a public health intervention.
Absolutely. Absolutely. So the history, it was first developed by electrical engineers and radar engineers during World War II for detecting enemy objects in battlefields. Completely different than how we use it now. ROC analysis since then has been used in medicine, radiology, biometrics, and other areas for many decades, and is increasingly used in machine learning and data mining research. So nowadays we always talk about ROC curve because of its relevance to the diagnostic tools that we have. So binary prediction problem, conceptual framework. So suppose we have a test statistic for predicting the presence or absence of a disease, right? This is definitely the sensitivity specificity, which you know, but I would like to highlight it in this presentation. So we have the true disease status, whether positive or negative. and we have whether the test turns out to be positive or negative. So if we test a person and according to the diagnostic test, he or she are positives, and in fact they do have the disease, then it is a true positive. And if they have positive results, but in fact they have negative disease status or they are not diseased, it will be false positive. If we have negative test, but if the person has the disease, it's false negative. And finally, it's true negative if the person turns out to be negative and in fact they do not have the disease. So these are the four diagnostic results that we might have, and two of them are false and two of them are true. So the P is going to be the total positive, the diseased basically, and the N will be the total non-diseased, and the total will be the total sample size. So what is accuracy? Accuracy is the probability that the test yields a correct result. And which ones from that table have correct results? It is the TP, true positive, and the true negative. So if we have the true positive and the true negative, we divide by the total sample size, it will be what? How accurate our test is. The higher, the better. How sensitive? Yes, exactly. So yeah, I'd rather use accuracy.
Rather than?
Well, rather than, because sensitive, it has different definition. So here we're saying, I don't care about whether it's a positive or negative as long as it is a true positive or true negative. So how many times does this test identifies the correct situation, right? And accordingly, do we usually use it? Not really. Not.
It's reported, but not.
Yeah, it is reported in general, but I don't care about. It might be the majority are true positives,
Yes.
very few are true negative, or the other way around, but it will add up to the same accuracy. But these two scenarios might be completely different. So I really want to know the positives and the negatives, the true positives and the true negatives. All right? So sensitivity is where I start focusing, instead of looking at the true positives and the true negatives, I start focusing on the true positives. So sensitivity is the probability that a true case will test positive. Who are the true cases? It is the TP and the FN, the true positives and the false negatives. So it's a conditional probability, if you remember what conditional probability is.
The whole horizontal.
لا.
False positive.
It is probability that a true case will test positive. So as if I'm telling you, among those who are really diseased,
How many?
what is the probability that the person will test positive? So it is the column, which is the true positives and the false negatives, which add up to how many people have the disease. Okay? So among those who have the disease, the TP are those who test positive. So it's TP over total positive people, right? So probability that a true case will be testing positive, also referred to as true positive rate or true positive fraction, but most of the times, or mainly, we call it sensitivity. Now, the other thing is focusing on the true negative. So I'm separating the accuracy into two, the true positives and the true negatives. Now, if I'm looking at the true negatives, it's among whom? It's among those who do not have the disease. So if a person does not have the disease, what is the probability that they will test negative? So it is Tn, true negatives, over the total non-diseased people, which is the Tn and the false positive. So false positive and false positive and true negatives are the denominator, and the numerator will be those who test negative. And this is specificity. We can call it true negative rate or true negative fraction. Now let me ask you a question. These sensitivity and specificity, what are they? Characteristics of what? Of the test itself, right? So it is the test, how good it is, by checking what is the capability of differentiating between the diseased and non-diseased, right? So it is purely a characteristic or a specific aspect of the test. Now, 1 minus specificity, what would it be? If I ask you, specificity is true negative over total. negative patients. 1 minus specificity, what would it be? Probability-wise. False negative.
1 minus specificity, false positive.
Look at it. So which cell is going to be taken? ما عم بقدر فوت Okay, so which column are we talking about when we're talking about specificity? The negative, the right side, right? So the negative group. So again, all my calculation is going to be on these negative people. And in these negative people, it is FPTN, false positive, true negative, right? These two groups, when I talk about specificity, it's true negative over the total, which is the N. 1 minus will be the other group. What is the other group? It's the FP, which is the false positive. Now, you got it? So 1 minus specificity, it's probability that a true negative will test positive. Do we use it? Are we interested in 1 minus specificity?
Yes, it's how bad, how...
How about, no, they will give us, no.
Why not?
Usually we can use it to spare patients from taking medications or because they will have a false positive test and they are actually negative. So we want it to be as low as possible to spare patients.
As low as possible. But can't you get the same picture by taking the specificity instead of 1 minus specificity?
Yeah, specificity.
When you're interested in 1 minus specificity, you want it to be low. Or the specificity, you want it to be high. So the specificity would increase the true negative, which is a good thing. The 1 minus specificity will decrease the false positive, which is a good thing, right? But why do we use it? We use it for the ROC curve. So I doubt that any paper would report a 1 minus specificity in the results. Nevertheless, whenever you want to do a ROC curve, you will have to report the 1 minus specificity. All right. Now, on the other hand, okay, I will. All right. On the other hand, I might be interested in what's this 1 minus specificity? We finished it. I might be interested in positive predictive value. So, what is the positive predictive value? Previously, we looked at the positives and we looked at the negatives, right? The true positives over the positives will be sensitivity. The true negative over the negatives will be specificity. Now I'm taking the true disease status as a denominator. But again, would it make sense to report these for patients? So in other words, if a patient goes and does a test and they come back with a positive result, they ask you, what do they ask you?
How lucky is I'm true positive?
Exactly. So the only answer you can have is by reporting, if you have the disease, you have 80% chance that you will test positive, but it doesn't relate to the patient because this is going to be a characteristic for the test. But I want to reflect it on the patient. So if a patient comes with a positive test, what is the probability that they will have the disease or not? So accordingly, instead of looking at the positives and the negatives, I want to look at the testing positive and the testing negative. And in this case, I will be taking into consideration the positive predictive value and the negative predictive value. What is the positive predictive value? The denominator is the TP plus FP. So true positive and false positive, meaning that all those who tested positive. Among those who tested positive, you can have two choices. Either the patient is in fact diseased or the person is not diseased. So a positive predictive value will be the TP or the true positives over everybody who tested positive. On the other hand, again, look at this. We are focusing on the true positives. But I want to focus on the true negatives. What would the denominator be? Exactly. So it will be true negatives divided by false negatives and true negative. Exactly. So the negative predictive value is the probability that a negative test will truly be disease-free. So among those who tested negative, what is the probability that a person will be disease-free? And it is true negatives divided by true negatives plus false negative.
So the answer of this, either for positive or negative, will be related to patients.
Absolutely.
That's when we actually give the number to the patient.
Absolutely. So when a patient comes to you and asks you, I tested positive in my test, what does it mean? What is the probability that I have the disease? If they tested positive, and let's say PPV, positive predictive value, is 75%, you will tell them there's a 75% probability that you do have the disease if you tested positive. It's more relating to the patient, not the test. So again, sensitivity, specificity are test-related measures. Positive predictive value, negative predictive value are patient-related measures. Now, look at this. If I have this criteria or this table, I have sensitivity being what? 27 over 100, right? So it's 0.27%.
0.27.
Yeah, 0.27.
Right, 0.27%.
Okay, so 0.27 or 27%, right? Specificity is 727 divided by 900, right? The, what's this? False positive, right? Or 1 minus specificity, look at this, what would it be? 173 divided by 900, or 1 minus 0.81. So it's 0.19. Accuracy, what do you add up?
27 plus 727 over
True positives, true negatives, divided by the total, it's 75%. But where is this 75% coming from? Here or there? I don't know, right? Positive predictive value, it is the positives
over 2.
divided by 200, which is the total positively tested patients. The NPV is the 727 divided by the negatively tested patients, and it's 0.91, right? Now, binary prediction problem, test properties, of those properties only sensitivity and specificity, and eventually the false positive, which is the 1 minus specificity, are considered invariant test characteristics, right? So these are characteristics of the test. Accuracy, PPV and NPV will vary according to the underlying prevalence of the disease. So you might have different numbers, different positive predictive value and negative predictive value based on the prevalence. But if you have a test with a specific sensitivity and specificity, by applying it on a group of patients who have 1% prevalence or 10% prevalence or 50% prevalence, do you think there will be a difference? The test characteristics are exactly the same no matter what. But the positive and negative predictive values will be dependent on how many people are diseased out of 100. So what is the prevalence? So sensitivity, specificity are thus fundamental test properties and hence are the most useful measures for comparing different test criteria, even though positive predictive values and negative predictive values are probably the most clinically relevant properties.
And meaning, sorry, a question, if it's related to prevalence, for example, you have a disease 8% prevalent in this population, so they can the PPV and PV ما في يكونوا أعلى من
إيه. They will change because you will be applying them. Okay, look at this. Here, it is the sensitivity specificity is over here, right? So it doesn't really matter if it is 1 to 100 or 1 to 99 or 2 to 98 or 10 to 90 or 20 to 80, right? The same characteristics are here because we're working with a column. Am I right? But when I'm working with the PPV and NPV, if I have 1 and 99, it will be completely different as if I'm talking 10 and 90. So the numbers, the PPV and NPV, will depend on how many patients are in the positive group and in the negative group because I'm going across them, right? And what decides on how many here and there? The prevalence, all right? In other words, the sensitivity, specificity are not affected by the prevalence. And when the prevalence is coming from here, right? Positive, negative. As long as I'm working within the positives and within the negatives, the prevalence doesn't make any difference. But when I'm working across the prevalence, every time the prevalence changes, the PPV and the NPV will change because the proportions will change. Make sense? Okay.
Can I add something?
Yes.
Perhaps students بيعرفوها. In relation to the clinical applicability كمان, you can generate more stable شو بسميهم characteristics or from the sensitivity and the specificity and the likelihood ratios.
Yes.
Likelihood ratio positive and negative. So likelihood ratio positive is sensitivity over 1 minus specificity. And it means true positive to false positive ratio. And because they are generated from these two, it will not change. And it is translated, if you have a test positive, then what is the likelihood that it is a true positive as opposed to a false positive? It's more stable than the negative predictive value and the positive. Likelihood ratio negative is the ratio of the false negative to the true negative. It is 1 minus sensitivity over specificity. So they're stable, مثل sensitivity or specificity.
Okay. Fine. So you understand this, why it is dependent on the prevalence. Now the ROC curves. Now assume that our test statistic is no longer binary, but takes on a series of values. For instance, how many of 5 distinct risk factors a person exhibits. What does this example mean? It means that the person might have 0 risk factors out of 5. It could have, it could be 1 risk factor, it could be 2 risk factors, 3 risk factors, 4 or 5 risk factors, right? Now this is a continuous value or a continuous variable. Clinically, we make a rule that says the test is positive if the number of risk factors meet or exceeds some threshold. So I say a person is at higher risk if they have 2 or more, right? Or 3 or more, or 4 or more, or 1 or more, right? So what am I using here? I'm using cutoff point to differentiate between 2 groups of people, positive and negative, okay? Suppose our previous table resulted from using x equal to 4, which is this table, all right? So who are the positives? More than 4 risk factors, and the negatives, less than 4 risk factors. Now, let us see what happens as we vary x. So, assume that I change the cutoff point from 4 to 3 or more risk factors. Are you with me?
Mm-hmm.
All right. So, according to this, everything changes. We still have 1,000 people. I still have the same positives, right? I have 900 here. I have 100 here, as in the previous table. I had 100, I had 900. Why? Because the prevalence didn't change. All what I changed here is the cutoff point. So would the sensitivity change?
No.
Okay, look at this. If I change the cutoff point, of course it will change, right? So what did I have before? 0.27, right? Now it's changed because the cutoff point has changed. Everything has changed. So the sensitivity now is 45 over 100, the specificity is 700 over 900, and you work out everything. So sensitivity increases, specificity decreases, and interestingly, both PPV and NPV increase. So you see the major changes that differed between using a 4 cutoff point or a 3 cutoff point according to the numbers. Now, you remember these graphs? Have you seen these graphs before?
It would change the sensitivity and specificity, but would it change it as...
Not for the test itself, not for the test, not for the diagnostics of the test. But what is our test here? What is our test here?
We changed the disease, the definition of
Exactly, the cutoff point changed. So the characteristic of the test itself is not, you're not talking about a glucose level where it has a specific sensitivity, specificity, right? You are talking about completely using a different definition. Okay, so look at this. We have 2 curves, people with the disease and people without the disease, or people without the disease and people with the disease. Most of the times they are overlapping. The more overlap, what does it indicate? The worse. Why?
those are false.
False positives and the false negatives. The less the overlap, the more clear the differentiation between the 2 groups of patients will be, right? It will be able to differentiate between them. Look at this. If I tell you I'll draw the test results over here, I'll draw the cutoff point over here, what does it mean? These will be labeled as positive and these will be labeled as negative. So what are all these people? True positives, because they are under this curve, which are positives, and they are labeled as positive. But what about these? False positives, because they are labeled as positive, but in fact they are under the negative curve. And the same thing here. Who are those? True negatives. And who are these? The false negative, because they do have the disease, but they are labeled as negative. Now assume that this moves this way and this moves that way with a little bit of an overlap. What happens? The false positive and the false negative would go down. So it will have less of an impact. And assume that this moves to this side and this moves to that side, so that the overlap is bigger. We have a bigger problem, right? Most of the times we have a certain amount of overlap that we try to find the best fit to it. Now again, this is the true positives, this is the false positives, this is the true negatives, and this is the false negatives. Now, if I move this line which identifies positives or negatives, what happens? Yani, in this case, okay, look at this. If I draw it here, if I move it this way to the right, what happens with the false positive? Decreases. But what happens with the false negatives? Increases. If I move it this way, what happens with the false negative? If I move it this way, the false negative will decrease. What about the false positives? Would increase. What about if I move it this way? What happens with the true positives? Would go up, right? And what happens with the true negatives if I move it this way? It will go down, right? So you see the trade-off that we're having? I increase something, I have to decrease the other thing, right? So what happens now if I change the cutoff point? Look at this. I don't have any what? Any false? What am I avoiding in this case if I go all the way here? The false positives. I don't have any false positives here, right? But I have a huge number of false negatives, and the true positives has decreased, right? Exactly. So again, if I change it to the other side, again, it all changes. So what do I want to do? I want to plot the sensitivity and specificity, because I want them to be the highest, right? But as I increase one, what happens with the other? Decreases. So I want to see how are they changing with each other to figure out a point where I have the best sensitivity and the best specificity. So I take what? I take different cutoff points. I take the first cutoff point here. This is sensitivity. This is 1 minus specificity, right? Exactly. So according to this, it's 100% sensitive. Why? It captured all the true positives, right? So it goes up here. But what about 1 minus specificity? It's bad. It's 50%, right?
So 1 minus specificity is what?
It is 1 minus specificity is the false positive. You remember that 2 by 2 table? We had the true negative, right? And the false positives, right? If I'm talking about 1 minus, I'm taking the other one. So if I move it to the right, so what am I doing? I'm starting to have false positive or false negative? I'm starting to have false negatives, right? So when I'm moving it here, these people are positive, but they are falsely positive. So it is false positive. What happens with the sensitivity? It starts going down. But at the same time, the specificity is increasing. When the specificity is increasing, what happens to 1 minus specificity? It is decreasing, right? So I have to start thinking now, sensitivity increasing is good. 1 minus specificity decreasing is good. All right? If I keep on moving it, it goes down, but this is good. It goes down also, right? I keep on doing this till I reach what? The point where I have almost zero sensitivity. Very small sensitivity. Why? Why do I have very small sensitivity?
We lost all the truths.
Exactly. Okay? So what do I do now? I plot them on a curve. So what is this curve telling me? It is telling me the different sensitivity and specificity for different cutoff points. So if you are a person to decide on what is the best cutoff point for this test, are you going to pick up this cutoff point here? Absolutely not. Are you going to pick up this? No. So most probably you're going to decide on one of those in the middle, which is suitable for your disease and for your cost of missing a positive patient, or the cost of identifying a negative patient as positive, and so on and so forth. Now, summary of all possible options. As we relax our threshold for defining disease, our true positives rate, which is the sensitivity, increases, but so does the false positive rate, which is the FPR. Can you see it? The ROC curve is a way to visually display this information. What happens with the sensitivity and the specificity, or the 1 minus specificity, with changing the threshold? So according to this, if I take 0, I will have 1 and 1. Is this good?
No.
False positive rate is 1, which is 100%. What does it mean? Almost everybody, right? So it's not a good cutoff point. When I change my threshold, my sensitivity decreases, but my specificity increased, right? Or 1 minus specificity decreased. And so on and so forth till I reach 6 here, which means 0% sensitive and 100% specific. But it doesn't help me by doing that. So most probably it is somewhere around here. Here I have 45% sensitivity and 80% specificity. You see why I'm saying 80? Because it's 20. Or I can be 73% sensitive and around 70% specific. So definitely this is better than that. Here I have 98 sensitive but 20% specific, and so on. On the test itself, yes, absolutely. And on the disease itself. And I think if you want to comment on the importance of the disease itself, in which cases...
So would you rather miss a case, or would you know, what's more deadly, or what's more costly, or what's more dangerous?
So typically when you are doing screening of for a disease in the population at a public health level, like congenital hypothyroidism, and you do not want to miss a single baby, we choose the test that will give you the highest sensitivity at the expense of specificity, and few false positive, which require further testing.
Okay. Now, what happens now when I connect these curves? It's very nice to have something like this. It's a clear cut, right? It's amazing if we get something like this. Nevertheless, most of the times we do not get something as smooth as this curve. Sometimes we get something like this. Okay? Now, what might an even better ROC curve look like? The diagonal line shows we would expect from simple guessing. So what does this mean? The diagonal line. It means as I am increasing the threshold, they inversely go in a very nice way. So it's just by guessing, right? The worst thing you can get is getting something very close to this. As we get away from this line, it will be perfect. So assume that we have a line like this.
Perfect.
What does it mean? It means whenever I'm increasing my sensitivity, what's the 1 minus specificity?
False positive.
Very small false positive. Even I reach almost a 95, 98% sensitivity with almost a 1 or 2% 1 minus specificity, or 98% specificity. Thus, for this point, it will be almost a perfect sensitivity and a perfect specificity, right? So accordingly, I prefer something like this. But most of the times, as we said, it is not like this. These are different ROC curves. This is 1, worthless. You see? It is really worthless, nothing. It doesn't help me at all. This is better, but this is very good. This is perfect.
The same as you.
Yes, exactly. So as I go to the extreme here, it will be a good differentiation. Now, the ROC curve allows us to see in a simple visual display how sensitivity and specificity vary as our threshold varies. And you understand now what is a threshold. It is the cutoff point that we use for dividing people into positives or negatives. Now, the shape of the curve also gives us some visual clues about the overall strength of association between the underlying test statistic, in this case, number of risk factors, and the disease status. So you would expect that this is showing me a stronger association or stronger relationship as compared to this or that. All right? Now, the ROC methodology easily generalizes to test statistics that are continuous, such as lung function or a blood gas or a glucose level or whatever. We simply fit a smooth ROC curve through all observed data points. In the previous example, it was 1 point, 2 point, 3 point, 4, 5, and 6, because we had only 6 points, right? 5 risk factors. Now, sometimes we might have a continuous one, so we might plot hundreds or thousands of different cutoff points and the sensitivities and specificities for these cutoff points, right? Not only 4 or 5 cutoff points, but maybe thousands of cutoff points. Now, area under the curve. So tell me, what do you think of comparing this and that? We have something called area under the curve. What is the area under the curve? Which curve is it?
The higher the better.
The higher the better. Why? Because the higher it is, the closer it is to the y-axis, right? So this line or this curve has a big area, but this has a lower area, right? So I can compare the area irrespective. I can add this 50% and add to it these remaining ones, right? So the total area of the grid represented by an ROC curve is 1. So if it is like this, or the whole area here is what? 100%. Now, the portion of this total area that falls below the ROC curve is known as the area under the curve. In this case, it is all this area. You prefer something like this, which gives you a huge area. And the smaller this area is, the closer it is to the diagonal line and the more worthless the test will be. The area under the curve serves as a quantitative summary of the strength of association between the underlying test and the disease status. An area under the curve of 1 would mean that the test statistic could be used to perfectly discriminate between cases and controls. Exactly, it will be like this, right? When would you expect something like this? When the overlap is almost non-existent.
Which is not biologic.
Which,
right?
exactly.
And we never see area under the curve
Of 1. Absolutely. So, an area under the curve of 0.5, what does it mean? Chance. معناتها diagonal line. So I have a diagonal line and all this area is 50%, thus it is useless. So reflected by the diagonal 45 degrees line is equivalent to simply guessing. Now, the area under the curve can be shown to be equal to the Mann-Whitney U test, or equivalently the Wilcox and Rank test, because, do you remember these tests? Non-parametric testing, yes. Non-parametric testing for what? What?
2 samples.
2 samples. It's equivalent to what parametric test? The T. Wonderful, T-test, right? So a non-parametric T-test, it is the Mann-Whitney, and it is equivalent to that. What is the continuous variable in this aspect? We have 2 variables. In T-test we have 2 variables, a continuous and a categorical. فينا نرجع للشارب.
Number having the disease, number not having the disease.
Yes, number having the disease, number not having the disease is what? The categorical. Or the disease status is the categorical variable. What's the continuous? It is the test itself, right? So I have a continuous variable, a categorical variable, a non-parametric test will be Mann-Whitney, and eventually the area under the curve will be similar to the Mann-Whitney. for testing whether the test measure differs for individuals with and without the disease, categorical, and the test measure is the continuous variable. It also equals the probability that the value of our test measure would be higher for a randomly chosen case than for a randomly chosen control. I will not go over this. So this is area under the curve. It's 100%. It's idealistic. It's non-existing. It is 50%. It means it doesn't help a lot. This is a very good test. This is an average moderate test.
And Hani, would you say that on the average, at least in my area of interest, this is more likely to be the 0.65? When
Yeah.
we get to 0.7, we say, wow,
Yeah.
we're
Yeah.
getting to 0.7. So in all, at least, I don't know about cardiology, but for a lot of, or pediatrics.
Yeah. I've never seen something beyond 0.8.
Oh, wow, 0.8 is really
Yeah.
good.
So most of the times it's 0.55, 0.60, 0.65. As you said, 0.7 is considered a very good test. Yeah. So, okay, again, you see this? What does it indicate? A certain cutoff point fully discriminate between positives and negatives, which is the distributions do not overlap at all. What is this? The distributions overlap completely. So you cannot really guess. You can guess, but you cannot really identify whether a person is positive or negative because they are overlapping. And it's the worst test. You see this one? It's very hard for you to differentiate between a positive and a negative. No matter how you use the cutoff point, you will always have false positives and false negatives. And accordingly, the area under curve will be almost a diagonal line. Yes? What?
You can put the cutoff this way.
Over here?
Obliquely.
Obliquely. Okay, I wish you can do that. All right. So again, these are almost very nicely separated, and if you do it like this, you will have very few false positive and very few false negatives, and eventually you'll have a very nice trend, and the area under the curve will be around 0.95. So what defines a good area under the curve? Opinions vary, probably context specific, and this is what we just discussed. What may be a good area under the curve for predicting COPD may be very different than what is good for predicting prostate cancer. All right? Because what is the cost of missing a prostate cancer as compared to COPD and all the clinical decisions that come into play. But in general, less than 0.5 is worse than guessing. Yani you'd rather guess rather than do the test. 0.9 to 1 is excellent, 0.8 to 0.9 is good, 7 to 8 is fair, 60 to 70 is poor, 50 to 60 is fail. Nevertheless, I can find you another reference which tells you above 0.7 is excellent, 0.65 to 0.7 is good, and so on. So really, the cutoff points for how good they are, it depends on different contexts, and you might find different references. From my experience, whenever you write a paper and you report on area under the curve and you say, I found a 0.72 and I consider it good, the reviewers will ask you, what is your reference for that? So you have to provide a reference for these cutoff points, and they are available in the literature.
And why, I think, why?
And why, yeah. Well, this is another one, you see, 0.97 to 1, it is excellent, and 75 to 92 is good, right? Because of different contexts and so on. Now, comparing multiple ROC curves, suppose we have two candidate test statistics to use to create a binary decision rule. Can we use ROC curves to choose an optimal one? So, you see these two? Do you think they are different? Yes. Do you think these are different? Not as different as those, right? What about those? It gets very hard. Now, in these two, you can see that this is better and this is better. Nevertheless, when you reach here, it's very hard for you to decide. They are overlapping, yes. So now, even the area under the curve most probably is going to be similar because it goes up here, it goes down here, this goes up here and goes down here. So most probably the areas will be very similar, and it's going to be very hard for you to decide on it.
So these are three different tests, for example, or what?
These are three different tests, yes. Yeah. Okay. Now, We can formally compare area under the curves for two competing test statistics, but does this answer our question? Area under the curve speaks to which measure, as a continuous variable, best discriminates between cases and controls. It does not tell us which specific cutoff point to use or even which test statistic will ultimately provide the best cutoff point. What do I mean by this? Look, if I'm looking at this, I can see that the area under this curve is bigger than the area under that curve, right? And I can see that the area under this curve is better than the area under that curve. But in real life, most of the times you have ups and downs. So assume that I have the area under the curve for this blue line and the area under the curve for the red line, and they are equal to each other. Is there any test you would like, the blue or the red, you would like to use? I'd like to report this one. Why? Because at this point, I have a higher sensitivity, but at the same time a higher specificity as compared to the green. Am I right? And this is what it means. It does not tell us which specific cutoff point to use or even which test statistic will ultimately provide the best cutoff point, but it tells you which has a better area under the curve, right? So whenever I statistically compare two measures, two area under the curves, it's not the only thing that I would like to take into consideration. I would like to take specific cutoff points and see which provides me with the best sensitivity and specificity. So there are two methods to compare the best cutoff point. So eventually, I would like to know which test provides me with the best cutoff points. There are two methods. The first method assumes that the best cutoff point for balancing the sensitivity and specificity, and you should understand now what does balancing mean. I want the cutoff point that increases my sensitivity and the specificity at the same time. I don't want a high sensitivity but very low specificity, and I don't want the other way around. So I want the point which gives me a good balance between both. So the first method assumes that the best cutoff point for balancing the sensitivity and specificity of a test is the point on the curve closest to the 0,1 point. Where is the 0,1 point? Here. Which is the point that's closest? If this is the closest, then this is the cutoff point that I would like to use, right? So, again, in this method, optimal sensitivity and specificity are defined as those yielding the minimal value of 1 minus sensitivity squared plus 1 minus specificity squared. So when I calculate the 1 minus sensitivity squared and 1 minus specificity squared, I would like to get the minimal value. The cutoff point that gives me the lowest number over here will be considered the best cutoff point. Make sense? All right.
But why is it, I mean, there must be a reason, right? I can't think of it immediately, but why is it 1 minus sensitivity squared plus 1 minus specificity squared?
Okay.
Isn't that how we measure distances and
Look at this.
axis?
So this point, how close is it? This is the sensitivity, right? But I want to get this part, so it's 1 minus sensitivity. Look at this point, it is 1 minus specificity, so, right? So I want to reduce both. If you go here, both will be reduced. Why do you take square? Who can tell me what do you want?
Isn't the distance between 2 points on a graph
Okay.
the difference between abscissa squared plus the difference between the...
Okay.
it's math يعني
Hey, why?
عكس اللي
Why?
هي.
We talked about it when we...
شيء هيك.
No. We talked about it when we talked about the standard deviation. Why do you square standard deviation? Standard deviation x
It might be on
I.
either side. It might be on either side.
Exactly. It might be positive and negative. If I add them together, they cancel each other. So I square it to get rid of the negative sign,
Sure.
to be able to get an absolute value. Okay?
The true distance is the square root, but we don't really care about that.
I want the absolute value. I want how close it is, right? So anyway,
Sure.
so all what I'm saying, I want to get the closest distance from the 0,1. The cutoff point corresponding to these sensitivity and specificity values is the one closest to the 0,1 point and is taken to be the cutoff point that best differentiates between people with disease and those without the disease. Sounds good? Now, there's another method. The second method may be used to determine the optimal cutoff point for a test is called the Uden's index. And I've never used this test. This method, I've never used it in my papers. I have good publications where I use the Uden's index, and it is very well accepted, and people use it because there's a reference to it. J, which is the Uden's index, is defined as the maximum vertical distance between the ROC curve and the diagonal or chance line, and is calculated as J equal maximum sensitivity plus specificity minus 1. All right? In other words, in the first method, I was looking at the distance here. In the Uden's index, I'm looking at the distance here. Okay? So, how do I calculate it? Using this measure, the cutoff point on the ROC curve, which corresponds to J, that is, at which sensitivity plus specificity minus 1 is maximized. Right? Now, of course, I'm interested in high sensitivity, right? And high specificity. But the curve is giving me 1 minus specificity, so I have to subtract a 1 for it to be able to get a big number for a good value. Is taken to be the optimal cutoff point, and an intuitive interpretation of J is that it corresponds to the point on the curve furthest from the chance. So the first method is closest to the 0, 1. In the second method, the Uden's index is the furthest from the chance line. Now let me open an Excel sheet to show you how things work.
Hanya, are you going to cover the C statistic? So,
Do you- I think we can combine it. Oops. Okay, look at this. I have here a person's age. Oh, nice. Good. All right. We'll do the very primitive.
Is it a PowerPoint?
Excel. Okay. Imagine with me. I have in an Excel sheet 2 variables. I have interesting. Okay. Okay. There you go. Okay. So I have here a code or an ID number. I have the age and I have thrombosis. What is the continuous variable? Age. And what's the outcome? Thrombosis. I want to figure out a cutoff point for age which gives me a differentiation between those who have thrombosis or develop from thrombosis or not. Sounds good? I have here people who have thrombosis and so on, right? So what do? What I do is I do this. Sensitivity and 1 minus specificity. If I take age at 7, what does it mean? Highest sensitivity but 0 specificity, right? Because at 7 it is at the left. So do I have any false negatives? Or do I have any false positives?
No false negatives.
No false negatives, right? Because a negative is a true negative, right? But what do I have? A lot of false positives. That's why the sensitivity is very high, but the specificity is very low. So as I am increasing the cutoff point for the age, right? What happens? The specificity starts increasing, right? Because here 1 minus specificity is decreasing, thus the specificity is decreasing. If I go all the way up, I have 0 and 0, meaning 0 sensitivity, but 100% specificity. right? So if you are to decide, look at these numbers, where would you pick up your cutoff point? I'm not going to go here, of course, and I'm not going to go here, of course, right? So where would you go?
The closest to the one
The closest to the
to the 0, 1.
0, 1. But I will not be able to do it لأنه I don't have 1 minus specificity squared plus the other one. I have sensitivity and specificity. The other method, the Newton's index, what does it tell you?
Just needs the specificity minus 1.
I have to have both maximized. Why? Because I want them to be away from the diagonal, right? So according to this, what are you going to be adding or subtracting to get this Newton's index? I want sensitivity. Add up these two.
These two columns.
Okay. Minus 1. So why am I saying minus 1? Theoretically, I want sensitivity plus specificity to be maximized. Am I right? But the fact that I have done 1 minus specificity, I subtract 1. So what do I want to add? 0.8 to 1 plus what? 1 minus this, right? Which is 0.3. Now, is this maximum? 1 minus 1 or 1 plus 1 minus 1. So this one, again, it's very small because 1 minus 1, this goes out and 0.8 would be the number, right? So
This column from this column.
look what I do.
B minus column.
What I do is, let me see here. This is the ROC curve that I did. Okay? So I take different cutoff points and I record these, and eventually I will have area under the curve. What is the area under the curve? It's 0.582. What is the p-value? 0.11 or 108. Am I right? Now, what is the null hypothesis for this? Who can tell me? By chance. Or the area under the curve is 0.5. Wonderful. And what is the alternative? It's different than 0.5. So what do you have? Not significant, meaning
Hmm?
It could be by chance.
it could be by chance. And what is the indication from the confidence interval? It's including 0.5.
Okay, small question. But sometimes the area under the curve would be 0.6, let's say, and still will not be significant. Because we take it as
What drives the significance?
the area.
The size of the sample.
The sample size, right? It's a very well-known theory. The more the sample size, even a small effect or a big effect will small effect will be significant, right? So in this case, it's exactly the same. You have the clinical significance and the statistical. You might find a 0.65, which is clinically important according to the cutoff points that you have from the literature. Nevertheless, it's not significant. Well, you have to address both statistical and clinical significance. Okay?
Yes, Hani, why didn't you do the column addition to pick up? Why did you look at the curve? Like if you go back to the previous Excel sheet you had, since
Yeah.
you said it's 1 plus specificity minus 1,
Yeah.
you have sensitivity. Sorry, it's sensitivity plus specificity minus 1.
Yeah.
You have sensitivity. You can figure out specificity and
Yes.
minus 1 and do the calculation and figure out what's the best one. You can do
Exactly.
that,
This
yeah.
is what I'm going to do. So if you look at this,
Okay.
I have the sensitivity, 1 minus specificity, and then I subtract 1 to get the specificity. So I'm reversing whatever I've done for the ROC curve. So I have 1 plus 0, 1 sensitivity, with specificity minus 1, right? So what do you see? It is increasing, of course, because according to the curve, I'm getting away from the chance line, right? But I keep on going away and away and away and away here, 0.1, 0.14, 0.16, and then it starts what? Decreasing all the way to 0, right? So what happens is, exactly, what happens is you want to pick up a Newton's index, which is the maximum. Here you can have 0.16 here, and you might have 0.14 and 0.17 So it indicates that you have multiple peaks, right? Most of the times we hope and we pray that we will have one peak that will stand out, and it indicates at this cutoff point you have the maximum sensitivity, maximum specificity, and you will pick it up. Whenever you have multiple points that have highest Euden's index, it is an indication that it is not a very clear, or the area under the curve is not very high, and you can see it. It was
But you have
0.58.
point. Why don't you pick up the highest?
No, you will.
Yeah.
You will, but it doesn't stand
It's
out.
not perfect.
Exactly.
Yeah, yeah,
So in other scenarios, you will have a very clear.
yeah.
So for example, I would have 0.17 drops down to 0.11, 0.1, 0.08, 0.6, and the other way around the same. And by this, you will have a very unique number. Fine. So
So it's like you want to have a bell-shaped curve of this distribution.
absolutely, absolutely, and the peak of it will be the highest Euden's index. Yes. Well, we can do an exercise if you all have the computers, or if not, we can skip it. But
This is great. Are you going to post this, Hannah?
yes, I will. So the first column is the patient coding number that you do not really need. The second column gives the age as a continuous variable. The third column is a categorical variable about having thrombosis, yes or no. Exercise, calculate the sensitivity and 1 specificity. You know how to do it from SPSS? I'll do it in front of you. Considering that age is the test variable and thrombosis is the state variable, calculate the ROC curve and plot it. Comment on the obtained results. Let me go and do it in front of you.
So can you just talk about the application of this in terms of public health and clinical research? So for comparing across tests for determining cutoffs.
Sorry, I missed that.
If you can just elaborate on the actual application of the ROC curve in terms of public health research and clinical research. So you do it, for example, to compare between what test you want to choose for a specific diagnosis, or to determine cutoffs for a certain risk factor related to a disease.
So I came across it for fracture risk assessment calculation. It's like the cardiovascular score or the breast cancer score. So we use something called FRAX, and we use 12 risk factors plus or minus BMD, and we have area under the curve statistics. But some other people have used simpler risk factor calculation and compared that performance with the one of FRAX. So when you review a test for performance, you come with an area under the curve, 0.64. So a lot of the papers I came across compared the area under the curve. Some of them said we compare C statistics, and honestly that's why I stuck to me, because I wasn't sure I understood what the difference between the two are. But for me, at the public health level, is I want to choose high-risk people. Should I use FRAX, which has a lot of risk factor, or should I use something that's more parsimonious with 2 risk factors, easier to use by clinical people, and gives me the same performance? So that's my experience with it. I don't know if that answers your question.
Yeah.
But I think
I have
now
never
maybe
done
the
this on
neonatal-
research purposes.
Yeah, but the neonatal analogy, which I like because it's screening and you want something that's very sensitive, you don't want to miss it. You can think of assays, right? So this first generation, the second generation, and the third generation, and when people say, okay, well, this is better, they're going to give you that kind of performance maybe, or just look at sensitivity and choose the test that's the best, or the generation test that's the best. Because I don't know if Anne wants to add anything.
No. Well,
So
Okay.
usually, when like some articles, they don't talk anything about the ROC curve and just talking about sensitivity, specificity, would you be able even to make clinical decision of any test?
it depends. If you are talking, shall I answer it?
Yeah.
Okay. It depends. What are you doing? If you are, if there is an established cutoff point and you are measuring how good it is in your population, something, or if you are measuring the diagnostic or a new test and you're measuring the diagnostic capability of this test, where you really need to identify a cutoff point, is something else.
So when you want to identify a new cutoff point,
You have to use ROC. You have to use ROC. And if you are not, then you can't. I'm not sure. I don't know.
And if it is an established test already, you don't need the paper to tell you what was the ROC sensitivity and specificity would be fine to generate, you know, for clinical application your likelihood ratios. بتاخديهم هيدول by the way. Yeah. Whereas if you are, you know, testing, researching a new test, you have to report all these.
Okay.
In the
Especially
same
the others.
population.
And this,
In the same population.
لا لا
because-
بالبيبر عم تحكي.
No, but I think if people are comparing prediction tools, Hani, correct me if I'm
Yeah.
wrong, and saying this is better than that, they can't do the prediction tool had a had an area under the curve of 0.64 in this study done in Australia and 0.58 in this study done in Lebanon, so this is better. No, because it has to be the same test in the same population.
Yeah, absolutely,
with the
absolutely.
areas under the curve. That's very important.
Absolutely.
And my problem with my review is not all of them were. A lot of them were in different population with different tests, and you can't tell.
Yeah.
Okay, very important.
So I just transferred the data into SPSS. So I have the age and the thrombosis. I go to analyze. I have something called ROC curve, right? So what is the test variable, as you all know? What is it? Age, right? The continuous variable. And what is the state variable that I'm working with? But what's the value of thrombosis? 1. So ROC curve with diagonal reference line, yes. Standard error and confidence interval, coordinate points of the ROC curve. I can ask for this. And under options, I can ask for non-parametric, of course, confidence interval, and so on. Let us see what it gives us. You see this table? This is what I use to calculate the Udens index. The only thing is that I do not know of any way that the SPSS will calculate the Udens index for you. So usually I copy it, paste it into Excel, and then work it out.
Wow.
Maybe it's primitive.
Data بيعملها؟
I don't know.
So Hani, go back. What did you do here? What did you pick?
Yeah. So yeah, sure. So here it is the different positives and negatives. So what? Okay. These are the area under the curve. Test result variation. Okay. So I go to analyze on the ROC curve and standard error and confidence interval. So I put here the continuous variable, similar to the t-test if you remember. T-test, I put the continuous variable and I put the categorical variable here and I specify which variable, which value. And under options, I can, okay, that's fine. And then I click OK. Okay, here is where it gives you the area under the curve with the significance.
You didn't have to choose area under the curve. You just had to choose your continuous and your dichotomous. You didn't.
Yeah, well, what I had to choose is the following. I want to check the order. Yeah, so if you do not select any of these, what it gives you, well, it gives you the area under the curve. The only thing it gives you is area under the curve, but it doesn't plot for you the ROC curve. Okay.
How can we, is there a way to, there's no way to find the best point in SPSS, right? Not the Uden or the first method.
Say it again.
Is there a way to find the best point in SPSS?
Not to my knowledge. Not to my knowledge.
So
No,
have
you
to
cannot.
calculate the Uden anyway.
Yeah.
So that's why you copy paste and go to
That's where. Yeah, I copy paste the output.
table. Yeah, the long
Exactly.
table.
Look what I did now. I put 2 continuous variables, although I don't have 2 continuous variables, but I took the ID as a continuous variable, right? Just to show you how to do 2 curves. All right? So according to this, what did you get? I get 2 area under the curves. You see them? One for age, which I found before, one for ID. Believe it or not, the ID is better. So I can divide people according to their ID and I'll be able to get a good sensitivity specificity.
But that's probably chance.
Yeah, I know. So this is age and theoretically, okay. Sounds good? So questions? Any questions?
So if we have like a golden standard of a
Mhm.
test and you are doing a validation of
Yeah.
another instrument.
Yeah.
So we can use the ROC curve to compare between the golden and
Yeah, well, ما هي لما when I tell you this person is depressed, right? I can't really measure depression except by a scale,
yes.
right? So I really need a very strong gold standard test that tells me this person is depressed and this person is not depressed, and I take it as the truth, which is the thrombosis. And then the new scale that I develop, I see how much is it picking up the people according to the scale.
And I can determine the cutoff of this instrument.
Of this new
based,
test, yes, yes.
yes.
Now, so the truth can be either a hard outcome, like thrombosis or death or whatever, and it could be a soft one. If a soft one, you have to have a gold standard to identify it. Okay? Any other questions? All right. So thank you very much. It was a pleasure.